Hey YouTube, it's Jay Kilroy. I'm back. Been working my butt off again, which is a good and bad thing. Today we're going to do kind of a combination video. I'm sure you're all familiar with the chip control videos that went around a while back that I really was a little out of the shop a bit much and didn't really participate in that. And then I get a lot of questions also as kind of the combo. I get a lot of questions on the diamond tool holder, tangential tool holder that I use a good bit. And we're going to do kind of a combo. We're going to do the diamond tool chip control. We're going to take the diamond tool holder here and we're going to put it to use on the revet here. Now this isn't a big monster machine like the pacemaker. This is just a 5 horsepower machine. Bit more oomph than your average 10K South Bend, but not a 18-inch monarch or pacemaker. So we won't be taking chips like that. But what we're going to do is we're going to take the diamond tool holder. We're going to get up close and personal with it. I'm going to explain to you how you sharpen the tool bits. It's easy. Explain to you the pluses and the minuses to this type of setup. Then we're going to take some cuts. We're going to take some cuts in some just mild steel here. We're going to take some cuts in some 3/16 stainless. Probably take some cuts in aluminum, and probably take some cuts in plastic. Aluminum and plastic being two areas where this type of tool holder really excels. Another thing we're going to do while we're doing all this is we're going to play around with the El Cheapo clip-on amp meter. This is a little Craftsman clip-on amp meter, model 82372. And I do a fair amount of work in the field, and that's what I bought this for. And it's so you don't feel bad about losing or breaking your $700 Fluke. Your $45 Craftsman does the same job. And what I'm going to do here is I'm going to use this in obviously clip-on amp meter mode with a max hold function. So as we start taking cuts, and we take cuts with various materials, I'm going to clip this onto a lead on the lathe motor, and we're going to get some idea of what kind of horsepower we're really putting to the tool, and what kind of horsepower it really takes to make that type of cut. That's another project I've got stashed off, been collecting parts for, is to build a load meter for this thing. So both of my lathes actually, which not that I push it, but just because it's interesting. So anyway, that's going to be kind of a little extra little piece of information that you might not normally get. So let me get the camera, move it in here close. We'll go over the tool holder itself and the details with the tool holder, and we'll talk about sharpening the tool bit. And then we'll put it on the machine, and we will make some chips. All right. This out of the way. This is the diamond tool holder, and you'll see it's called a tangential tool holder because it holds the end of the bit tangent to the cutting circle of the workpiece. These are not new. These have been around for well over 100 years. There's evidence of there's records of patents and designs and advertisements for these types of bits, these types of holders going back well over 100 years. Some of them pretty impressive in size. You can hold a square tool bit, as I have here. You can also hold a round tool bit, which a round tool bit gives you a really nice cutting surface, gives you a really nice tapered cutting surface, which allows you to get fabulous finishes on materials when you don't have to worry about cutting up to a shoulder or you know, cutting up to a sharp edge. So if you're just turning and facing without worrying about any shoulders or edges or anything like that, use the round tool bit, because it makes it even easier. These are sold, this one here was sold by a company called Baycom. They're a distributor, and the link's down below. They're a distributor for a company called Eccentric Engineering, which is an Australian company which makes this design. This one I've had for quite a few years. It is the 16 millimeter or 5/8 size, which used to be the largest size they made. They now make a 20 millimeter size that I am really interested in getting a hold of, that uses a 5/16 there we go. I'll hate doing that because I'll have to reset my center height here in a second. It uses a 5/16 bit. This one here, a little bit. This one here uses a 1/4 inch tool bit, or a 1/4 inch round. And this is a piece of T15 tool steel. It's a Rex T15, which is a cast tool steel product. So it's very, very good. Has really high heat hardness as far as cutting goes. The downside is when you grind it, do not quench it, because it does not like thermal shock. But like I was saying, these things have been around for a long time. This one was bought from bay.com, bay-com.com, their distributor here in the States, quite a few years ago. They also make a left and right hand model now, which they didn't at the time, and the prices have come down. Actually, you can get a set of these now, right and left hand, for about the same that I paid for this. Actually a little less than I paid for this. I paid about $150 for this tool holder here. You can get them for a little less than that. You can get them for probably about $100 a piece in a set, and they are mighty handy. It's a real, if you do a lot of plastic work or aluminum work on a older machine, or a machine that doesn't have extremely high speed capabilities, then high-speed steel is your friend, because you can get a surface finish that your older machine isn't going to allow you to get with carbide, because you're not going to be able to get the surface speed up to where you need to, say, effectively use some of the modern insert technologies, like these special aluminum inserts, super sharp aluminum inserts, or diamond coated inserts. You need a machine that has the velocity to use that. So you saw me take the bit out here, the cutting bit. I fully expect that this one cutting tool will last me the rest of my life in normal use, because when you sharpen it, you take so little away. All you do is sharpen right across this flat surface. You just sharpen a little of that back, and that's it. So you there's no reason for this not to last quite some time. It's probably 3 or 4 years old as it is, and I use it all the time. So let's get set up with the grinder, and let's put a little touch up on this before we start making chips. Alright, here we are at the grinder. It's the old Baldor 12x2 2 horsepower grinder. And we've got the tool bit mounted in the holder that comes with the diamond tool holder that helps you hold the right angle. And it's a pretty simple affair. And you just want to make sure that your tool bit is on center line. The center of your tool bit is on center line with the center of your wheel. Otherwise, you'll cut a concave surface on it, and it won't be quite what you're looking for. And this is really easy stuff here, right? Move it back and forth across the wheel a couple times, and you're fresh. That baby is sharp. Remember, with T15 and this type of tool steel, don't quench. Let's go ahead and cut it off and go back over to the bench. All right, we are sharpened and hot, so watch yourself. Let's get the tool bit mounted back in the tool holder here. Cinch it down a little bit. Easier to tighten that up once you get back in the tool post. I'll go ahead and tell you the biggest downside to this type of tool holder is that every time you remove the tool bit for sharpening, you have to readjust center height. Unlike with a more modern carbide insert, swap an insert and you're right where you left off. The other downside to this tool holder, I would say the only other serious downside to it, is that you can't set the tool holder. If you set the tool holder, well, let's put it on the lathe. It'll be easier to explain this to you here. All right, we got a quick edge on the little tool bit. Before we get started, I thought it was maybe smart to go over a little bit about high-speed steel terminology and the kind of the stuff you see in the in articles and in catalogs. And I'm going to post a link to a really nice write-up right here. This was done by the by ASM International, published in 1989, kind of ways back, on high-speed tool steels. I'm not claiming authorship to any of this. This was done by Mr. Alan Bayer and Bruce Becker. They both worked for Teledyne Vasco at the time. But this is a great write-up on high-speed steels, what's in what the terminology means. One of the things that you might find interesting is that the number after the M or the T, when you see things like M40 or M42 or M30, you see these different numbers, or T1 or T5 or T15. You see these different numbers behind these letters. The numbers mean nothing except to differentiate between one type of tool steel and another. M42 is not, quote, better than M30 or M40. It's just different. You have to look at the material properties of the tool steels in question to find out if they suit your purpose. Now, that being said, I kind of take a shortcut, okay? Tool steels that begin with M have moly in them, and they are tougher and more abrasion resistant than tool steels that begin with T, which have tungsten in them, which are harder and ultimately have higher high heat strength than the M tool steels. But if you're doing interrupted cuts or nasty abrasive material, or you're cutting the scale off of some funky hot rolled or whatever, the M tool steels are your friend. If you are doing turnings in in stainless and other hard materials, and you're not doing interrupted cuts, then the T series tool steels are your friend, because you can turn faster and you can run them hotter without damage. But that's just kind of a general overview. Again, the link to this article right here will be down below. Now briefly, when we start cutting, we're going to have some kind of ongoing discussion about speeds and feeds. A machinery handbook is your friend. This is where you learn about speeds and feeds. If you do not have one of these, you need one of these. I have one that's relatively new. I have several actually, but this is the one that I use because it's the large print edition. No laughing. That's all I gotta say. It's the big hardback. It's not the little book, right? So I can read this, and it's still pretty small type. But if you turn back in your Machinery's Handbook, you'll get to a section on machining operations. The first section in machining operations is cutting speeds and feeds. Everybody's kind of gone over this stuff, talks over this at time of meeting, so I'm not going to get into any great detail about it. But there's a lot of reference material here, so get you one of these. Other than that, I use two formulas that I pretty much have committed to memory when I don't have a senior moment. And we'll go over them real quickly, and I will put them down here in the video so you can jot these down. And these are pretty quick and easy formulas for calculating either the surface speed for your current RPM or for calculating the needed RPM to get the surface speed you want. To get the surface speed of your current RPM, you're looking at RPM times diameter times 0.26178, which is actually pi divided by 12, right? But why worry about pi divided by 12? RPM times diameter times 0.26178 will give you surface feet per minute for that combination. If you want to go the other way around, as you might expect, it's surface feet times 3.1897. This is pi divided by, this is not 12 divided by pi, this is pi divided by 12. This is 12 divided by pi, excuse me, divided by diameter. And that'll give you the RPM that you need to get the surface speed you want. Most high-speed steel cutting, if you look in all the various publications, including this one and all sorts of stuff on the internet, people are going to tell you anywhere from 50 surface feet per minute to maybe upwards of 120, 130, depending on the material you're cutting and depending on what you're cutting it with. Now this is for high-speed steel, this is not carbide. So what we're going to do is we're going to do a little cutting right here, right off the bat, where we're going to crank out, we're going to cut some 316 stainless with this little piece of T15, and we're going to start out at 130 surface feet per minute. So we're already at the top end of what some folks find acceptable. And again, we're going to use our little amp meter to see what kind of load we're actually putting on the machine, and then we're going to go from there. The piece that I'm starting with, I'll move the camera. Okay, the piece that we're starting with here is a piece of 316 half-inch diameter, and we've just sharpened this tool bit. We have to set our center height, and we're going to do it the ABOM 79 approved method, which means we're going to line it up as good as we can by eye, and then we're going to face until we get no pip on the face. That is an old school method, and it also happens to be the method approved by Adam Booth. So my buddy and a guy that definitely knows how to make some metal chips fly on the lathe. So first thing we're going to do is we're just going to line this up and get close. I am definitely low. Like I said, this is the only downside to the diamond tool holder, is having to reset center height on a regular basis. The other thing you'll notice, when your tool post is mounted parallel to the front of the chuck or are perpendicular to the workpiece, as do a lot of people mount theirs, you can't face. You can turn, but you can't face. This is another downside to this particular setup, but not a terribly bad one. Let's move around here. As most of us do, you know, sorry about that, I keep a wrench right around to adjust the position on my tool post so that I can face. And if I used a 40 position tool post, I probably would need to do that. Anyway, so what we're going to do is we're going to face here until we get no pip, and then we'll know that we are on center height. So we're running at, I'm going to get it up to right at 1,000. That's as close as I can get it. So we're running about 1,000 RPM here. And it seems that I got lucky on my center height adjustment and nailed it right on the money. So we're going to tighten this up. We're going to face this off. We're going to extend the workpiece a little bit. We're going to get a couple of cuts. Now, I'm right now with the machine running at 1,000 RPM with no contact to the workpiece. My amp meter says I'm pulling about 8.5 amps. So let's face this off. Alright, I'm going to cut the machine off there for a second just so you can see this. This is a beautiful finish we're getting here. Again, we're cutting 3/16 stainless with high-speed steel at 130 surface feet per minute. So we're not taking big cuts here, but that's not really what we're trying to figure out. What I'm going to do now is I'm going to crank the RPM up to about 1,500, and we're going to take the same cut, see what happens. Alright, turn the workpiece around so we get a full 1/2 inch. I'm going to crank the RPM up to 1,500. We're going to leave the feed the same, 6 thou per rev. We're going to take another 40 thou cut. We're going to measure our motor amperage while we're at it. And we're going to see how this goes here. It's kind of loud with the feed going at this RPM, so don't expect to hear much from me. Alright, what did we learn there? 1500 RPM is way too fast. There's some definite decoloration along the cutting edge of the tool bit. And this is with stainless steel, 316 stainless. There was definitely some discoloration. And got a really bad surface finish. There was a lot of pushing away of the workpiece. If you probably saw when I pulled the tool back, it cut. So there was a lot of pushing away, probably some climbing of the workpiece. May have changed if we use a tailstock center, but you know, a 50% increase in speed is a 50% increase in surface speed. So we were at about 130, say 65, add 65 to that again. 65 is half of that, so add that again to the 130. So we were around 195 surface feet per minute. And I'm just going to call that as too much for stainless steel and high-speed steel. So at least with this T15, this Rex CPM T15 that I'm using. So what we're going to do now is I'm going to touch the tool bit up. We're going to get it back in the tool holder, and we're going to start taking some cuts in this stainless and look at more of depth of cut performance, taking some healthier cuts at some slower speeds and feeds, and see how the diamond tool holder performs while gnawing off some material, and also continue to take some amp readings. The machine idling at 1000 RPM with no load on it pulls about 8.5 amps, and this is at for some reason this evening my high leg is running around 210, but about 240 volt service, 230 volt service. So 8.5 amps is that's 1900 watts. Using a number of 765 watts per horsepower. That's about 2.5 horsepower. When I was taking the first cut at 30 thou, and the 30 thou and the 40 thou are basically the same. When I was taking the facing cut, it went up to about 10.2 amps. When I was taking the 30 thou and 40 thou cuts at 1000 RPM with 6 thou feed, we were running about 14.2 amps. So that's right at about 5 horsepower. I don't know if this is just generous, but there's a lot of waste in that system. That doesn't mean we're getting 5 horsepower to the spindle, obviously not. The Reeves drives waste power, all the belts waste power, everything. That's just the total power being consumed by the system. That was about topped out. So now we're going to move on, and like I said, we're going to freshen the tool bit up, we're going to put it in, we're going to take some deeper cuts. So let's see how that goes. cut you just watched there was a 100 thou in 316 stainless at about 700 RPM or so. Feed was 4 thou per rev. Let me go check the old amp meter. Alright, the amp meter says we pulled 14.2 amps on that cut. We're going to leave everything else the same. We're going to go back and do 150 thou. Again, this is 316 stainless that we're cutting here. Okay, that's making a nice smooth cut, fairly drama-free. It's making a 5-mile long hand shredder of a chip. And the chip's coming off tan and turning blue in the pan. And at about 700 RPM, 316 stainless. This actually is behaving a little better. All right, now that's hot, but unlike the higher speed cut we had earlier, I don't have any discoloration of the cutting edge, even though we were picking a pretty stout cut for this material and this type of cutting tool. The machine's definitely capable of taking a deeper cut than that, but one of the things you have to look out for with the diamond tool holder is making sure that this screw here on this side that holds the tool bit in place is tight. I guess you'd kind of consider it a safety feature. If you start taking too heavy a cut, it'll push the tool bit down in the tool holder and decrease your depth of cut as long as you're on center. If you're above center, it'd be real bad. It wouldn't cut with a flip anyway. So I guess you could kind of consider that a nice feature, especially for someone that's just starting out in machining or is machining at home. So anyway, that is not terribly bad. So I'm going to turn the workpiece around so we can get a bigger piece, and we're going to try another cut. All right, this is the last cut we're going to take in the stainless material here. I'm going to go ahead and we're going to leave all the other settings the same, and we're going to take a 200 depth cut here for this last cut in 316. Okay, that shows that that's perfectly doable cut. Again, I don't have any discoloration here on the cutting tip. And zoom out a little bit. You can see that's a dang hot workpiece. I could brand myself with that baby, so I'm not going to be grabbing it. All right, that cut there is finished. That's 200th off the diameter, or 100 aside, and that's a in 3/16. That's a pretty healthy cut for a machine of this size and horsepower. Measured checked my amp meter, and the amp meter says I was putting out about a little over 5 of the 5 available horsepower that I had. So told me I was pulling 21 amps. Now there's plenty of loss through the Reeves drive and stuff like that on a machine with a variable speed. But as far as total power consumption goes, that shows that I'm working the machine pretty fully, pretty near capacity as a 5 horsepower machine. So let's get the cutting edge cleaned up here, and then get us a piece of mild steel in here, and let's make some mild steel cuts. Alrighty, so I've decided to pretty much call it an evening. As you can tell by the window, it was light when I started and it is now dark. We've taken quite a few cuts in the stainless steel piece that I had here, a work piece, and the diamond tool holders performed exceptionally well as far as I'm concerned. Done very well. Anyway, I'm going to do another video, follow this up, and we're going to cut tool steel. We're going to cut tool steel. We're going to continue to cut with tool steel, and we're going to cut some cold rolled and some aluminum. And so look for the link, Dropbox link to this document here. This is the Teledyne Vasco high-speed tool steels document. This is a great read. Look for that down below. Look for the links for the bay.com, where you can get a diamond tool holder. No affiliation, just a satisfied customer. And I'll include a link for the Eccentric Engineering. This is the Australian company that actually makes the diamond tool holder. You can see the full range of their products there, including some of the larger sizes that I don't have. They have a 20 and a 25 millimeter shank for people who use inch size tool in larger machines. So maybe nice if maybe we get a diamond tool holder for the pacemaker. So I'll be back with you soon. Be safe in the shop.